Standard physics models often treat the light cone as a flash of light expanding through a pre-existing container. Mathematically, the cone represents a local separation determined by a metric of signature negative, plus, plus, plus. It differentiates directions that carry massive bodies from those that carry massless signals, or those that cannot communicate at all. This local structure generates the geometry of spacetime rather than inhabiting it. The assembly of these permissions across a manifold dictates the global architecture of possibility. We are investigating whether mapping the order of events provides the information necessary to recover the conformal geometry of the universe. Understanding relativistic possibility requires reconstructing the Lorentzian metric using the properties of order and scale. We begin by removing the coordinates. Discard the idea of the manifold and its x, y, z, and t axes. This leaves a bare set of events, discrete moments without inherent distance or duration. We introduce a partial order relation. This is a mathematical rule determining which events precede which. The order is partial because some events lack a sequential relationship. This gap in the graph represents space-like separation. This skeletal graph of precedence provides the information from which measurable reality emerges. Focus on the tangent space at a single event. Here, a Lorentzian metric takes two tangent vectors and returns a scalar. The sign of that scalar sorts all directions into three invariant classes: time-like, null, or space-like. The null vectors form the boundary of the cone. Proper time fails to parameterize these trajectories, as they represent massless signals in geometric optics. We can test this structure by applying a conformal scaling, multiplying the metric by a positive smooth scalar. This transformation stretches or shrinks lengths and clock rates. However, the sign of the vectors remains the same. The boundary of the null cone is immobile. The local light cone dictates the limits of causality while remaining blind to size and duration. We now observe multiple events across the manifold. A chronological relation exists if a future-directed time-like curve connects 2 points. This is a partial order. Unlike ordinary time, it does not force every pair of events into a sequence. Space-like separated events are incomparable. Neither event lies in the other's causal future. We can define sets for the chronological future and the chronological past. The intersection of these two sets generates the Alexandro topology, forming a causal diamond. This diamond identifies the finite causal region containing events influenced by the first point that can also influence the second. These overlapping diamonds provide the formal expression of relativistic simultaneity and its non-absoluteness. The 1977 Malament Reconstruction theorem addresses bijections that preserve chronological order. If a mapping preserves these arrows in both directions, it also preserves the causal diamonds, forcing the map to be a homeomorphism. This identifies the conformal geometry of spacetime using only the causal order of events. However, pointwise cones can still allow for global pathologies, such as an observer returning to their own past. To prevent this, we apply the causal ladder, a set of global conditions required for predictable evolution. Global hyperbolicity is the decisive condition. It ensures every inextendable causal curve is met exactly once by a Cauchy surface. This surface allows for a future domain of dependence, where data on the slice determines the evolution of the future. While local light cones permit causality, global hyperbolicity provides the global organization required for deterministic physics. Causal order provides the conformal structure, but the metric remains unfixed. We are still missing the scale. Two metrics with the same cones differ by a positive scalar field. A volume density detects that missing field. It fixes the remaining local scale. Causal order joined with volume data recovers the Lorentzian metric. Causal set theory applies this logic to the quantum frontier. This approach proposes that a discrete partial order is the microscopic source of spacetime geometry. The links between discrete elements provide the geometry, and the number of elements provides the volume. Relativistic causal structure identifies the possible paths for signals and particles. It is not an explanation of physical causation. This architecture also differs from the indefinite causal order found in quantum information experiments. Operationally, indefinite order doesn't require removing the local null cones of a background spacetime. The causal structure identifies the geometry of accessibility and the limits on possible influences. The Lorentzian light cone defines the distinction between possible communication, temporal development, and forbidden influence.